want you to try to tap into last year in your brain and be like, what transformations occurred?
That's gross.
All right, what's the table for the first one? It should have been easy, yeah? What is it? Standard parabola, right? With our vertex at the origin, we have our 1, 1, we have our 2, 4, sorry, negative 2, 4. We have our 1, 1 and our positive 2, 4. We can continue, right? He's just a normal parent function. Okay, what happened with the next one? Fill in my table.
13, 7, 0, 7, 13. It's 5. It's 5.
Oh, yeah.
It's 5 instead
5
of 0,
is,
I
I
believe.
believe, yeah. Or wrong, I'm not mistaken.
Yeah, it should be.
13, 7, 5.
Yeah.
Yeah.
Okay. Hey, look, they're both symmetric, right?
Yeah.
Because this one folds, you can see it right here. There's the vertex. How did I figure out that the vertex was at 1 instead? Do you see how my tables are centered differently? How did I do that? Interesting. Let's keep going. So what happens when you graph? Can have it over just a little bit. I have my negative 1, my 0, 1, 2, and 3. I have 13, should be way up here. 7, 5, 7, 13-ish. All right, what happened to him? Talk it out. He shifted to the right, and he shifted up, and that was it?
No. Yeah.
And it's stretched by
How?
2 over 1.
What kind of stretch?
Horizontally.
No,
Vertical.
Vertically.
Oh. It's a vertical stretch.
It's a vertical stretch, but why?
Because it's not
Hitting the.
What was the change in y's from the vertex to 1 point removed? Just 1, right? It was 1 away, then it was 3 away from there. But what's the change here?
2.
2 away, and then what?
5.
6 away. Huh. Wait a minute, does that make sense?
So horizontally stretched by 1 over 2.
This was 1. This was 3 with our delta, right? And what's this one? 2. And what's this one? Why does that make sense?
Because that's proportional by 2.
The y's got doubled, or the change in y's got doubled, so it got vertically stretched. Anyway, this is all discovery. Technically, if you have some nasty function in homework and you can't figure out what to do with them and you're not allowed to use your calculator, could you play around with the table? Yes. Is it always super helpful? Hopefully we can do better than that. So let's start doing better than that, huh? I'm going to start with reviewing shifts. So back in our composition book, new section, new site, 1.7. Nice thing is, a lot of you are already like, hey, we've kind of talked about this before last year. And you're most definitely correct. But when I said something about it yesterday, there were a lot of groans. Which means we've seen it, that doesn't mean that we like it.
I like it.
You like it? I have a little battery. Hello. Ooh. I'm just getting there. 19%? Can you make it? We'll try. All right, do you guys have to literally write every single word on this? No. No, no, no. But first of all, shifts. Do shifts distort the graph at all? It's just a shift. The only transformation is a translation. Is the graph distorted? What do I mean by distorted?
Like changing the
Stretch
form
or
of it?
Changing the form of it, stretching, compressing, reflecting. If it's shifting, no distortion, right? Merely a move, as the name obviously implies. The shape doesn't change. Now this whole little table is just basically saying let C be a positive real number. So we're saying, okay, we're adding a positive real, we're subtracting a positive real. But if we have a function with an addition on the outside, that's going to be a vertical shift up, right? If we have a function with a subtraction on the outside, that's going to be a vertical shift down. Why vertical? Pourquoi? How come?
Oh, because it's on the outside.
It's on the outside. And who is f of x? These are the
Y.
y's. The y's of the function. So the y's are getting or adding c, or the y's are subtracting c. Remember how to remember? Because in the next example, ooh, it's no longer on the outside. Where is it?
Inside.
On the inside, it's happening to the x's. So my x's are shifting. Now why is this weird? Horizontal shift to the right. Remember?
Oh yeah, horizontal is opposite way.
Uh-huh. Horizontal is opposite what you think. Vertical is the same as what you would think, naturally. So x minus c, there's x minus a number. It's going to be to the right, and if it's x plus c on the inside, horizontal shift to the left. This is just to have you guys remember. I'll give you a couple more seconds. It's going in your notes, but hopefully where is it going to stick? Brains, yeah, exactly. It's going in your notes now, hopefully it's sticking in your brains later. Now the nice thing is, before we move on though, for the entire section of transformations, trying to keep straight the vertical ones from the horizontal ones. The vertical are always going to happen on the outside. The horizontal are always going to happen on the inside. So if it does help just a little bit to visualize color code, etc., you could always think, I have vertical on the outside of my function, vertical on the outside, horizontal on the inside, and horizontal on the inside. Okay? Let's see, one more thing for us to, do I have examples? Oh, I do have examples. Okay, we'll go there. You guys ready?
Yeah.
Okay, so then if I was to go ahead and write down an example, I could do it two different ways. One way is I could give you like a random graph and say, hey, do this transformation to it. And that way I wouldn't even tell you a function. Or I could just give you something like graph g of x is equal to x cubed minus 1. And how could I expect you to be able to graph that? Or just to have, we'll leave it. We see the shift, right? How would you verbalize the shift?
1 unit down.
Down 1, but who's going down 1?
Vertical translation.
Vertical translation, down 1, but who's going down 1?
The whole, the x cube.
This is f of x. This is my parent function. So why did we do all of section 1.6? To hopefully know who he is and how he acts. Who is x cubed? What's he look like? He's a spooky soup one, right?
Yeah.
So if we're just going to sketch it, we could go ahead and, well, wait a minute. Where was his important point?
That word.
It was at the origin, so we're just going to take the origin and shift it down 1, right? And we can approximate. Now how can we make it better? We could do a table. We could do a table, but would we need to change the x values, or could we keep it like -2, -1, 0, 1, 2? Yeah, we can keep it, right? Because it didn't horizontally shift. But what if I was to do something like, instead, no, I can't do that yet. You guys aren't ready. Okay. Describe. What's the transformation of the green one?
Vertical translation.
Ooh, not vertical, it's under the square root.
Oh.
You see it? Who's the parent function?
Yeah.
Root x. And where's the plus 1?
Inside.
Yeah?
Yes.
If it was outside, that'd be vertical. So since it's inside, it's horizontal. And since it's horizontal, we're moving to the
left.
left, right? Oh, but who was square root of x and what did he look like?
It looked like that, like,
He was like the little swoopy swoop, right, from the origin? Okay, so what am I gonna do with him?
move to the left.
Move him one to the left, and then I can have pretty much the exact same. Now, if I was to do a table, remember, for this one, tables aren't necessarily always bad. I think they're looked down upon a lot. Like counting on fingers, but actually people who count on their fingers are smarter. Anyway, or they are shown to have a new study. Have I already told you this? I think I've already told you this. There's a new study out that people who learn to count on their fingers usually end up having more success in math. Go figure. You're like, hey, so got this. But anyway, this one, remember the -2, -1, 0, 1, 2 was totally fine if you did need to go that route. But this one, where would we put this instead? Well, hold on. Square root of x usually starts where? The origin. So instead of starting at 0, we're going to start at -1, yeah? We could do like 0 and 1 and 2. So we have to consider a few different things if we even go to a table. It's a not bad technique to go to a table if you need to get a picture. But you still need to think of the square root function starts at 0. Oh, it's shifted, so I'm going to start at -1 if we need a precise picture, right? Let's keep going. So we have a vertical shift and we have a horizontal shift, and of course we could put it all together and have something a little bit more fun, but now we'll keep going. Good? Some of you might have thought we were going to dilations. Let's save that until the end. Let's go to reflections. Reflections. Does the shape change? No. But what does change? The direction is one way of putting it. The orientation is another way of putting it. Reflections or mirroring. The shape doesn't change. There is no stretch, there is no compress. But the orientation or the direction does. Another way of thinking about in the x-axis is like about the x-axis. What's happening to the outside or to the inside to get that reflection? There's a negative, so the sign is going to change. So if it's on the outside, the sign's going to change one way, and if it's on the inside, the sign's going to change another way. It's being multiplied. So a negative by the outside, a negative by the inside. Now, but a second ago we were talking about how on the outside means vertical, right? But what do you see in the wording? I see x. That doesn't make sense. Aren't x's horizontal? Unless you think about, doesn't reflection about the x-axis mean that we're doing like an up-down flip, right? So this is going to be a vertical flip. What was up is down, and what was down is up, and we'll see that in a second. And then the next one, on the inside, horizontal. Where's it going about? It's just like a little rotation arrow, just to think about mirroring going to the other side. It's going across the y, which means it's going to be a horizontal flip. What was on the right is going to be on the left. What was on the left is going to come over to the right. So does our outside, inside still work? Uh-huh.
Yeah.
Just the wording is going to be a little funny, because a vertical flip means across or in the x-axis. And a horizontal flip, we would say in the y-axis, because it's going about the y-axis. Ready for examples?
Ready. Sure.
Okay. So what if I was to ask you to graph let's do y equals you can use a table if you would like. Thinking about absolute value and how he behaves or acts. How would you graph him? How would you graph him? Who's our parent function?
X.
X inside the, what are those? Absolute value. What does that graph look like from yesterday? You can look back if you need to. What's absolute value look like? He's the V, right? Plug in a 1, get out a 1. So if we want to think about who was there before, plug in a 1, get out a 1, plug in a 2, get out a 2 of normal absolute value. I'm just going to do dotted. That's absolute value of X. -1 is also a positive 1. -2 is also a positive 2. Okay, what's happening to him? He is being flipped. Flipped how?
It is going to the left.
Across the, it's on the outside, so we're going to flip it down. Does that make sense? A vertical flip? So on the outside, we're going to flip down. But what else is going on? I heard someone say horizontal, and I like it. Keep going.
The horizontal.
Horizontal shift, and I'll just say left, which means horizontal 1, right? So now can we maybe graph this a little better? So if we were to go down, we would have it here with 1, -1, 2, -2, -1, -1, -2, -2. And then to get the entire graph, you could say down 1, left 1, down 1, left 1, down 2, left 2, down 2, left 2. There we go. Now, does your graph start to get really complicated if you're graphing all the pieces? Yeah. But is it good still to think through the pieces as far as what's the parent function? What happens? What happens? Okay, there he is. Once again, we can use a table if we need to. But if we can visualize the parent function and then do each of the transformations, it's usually a little easier. Jesse?
How do you get the parent function again?
You have to look and ask yourself the question, what changes occurred? And I see the +1 on the inside. I think technically I was showing those with blue. I see a +1 on the inside, which is a shift. I see a times a negative on the outside. Take those away, and what's left? He's the parent function. Does that make sense?
Yeah, but like, how did you know how to graph?
Back from section 1.6, if we were to go back, I think absolute value, wasn't he one of ours? Oh, he was the last one. There he is. Sorry. Yeah. So then it was just one of those, and you can even think of, technically, if I were to come back here, he's one that you want to get familiar with, but if you needed to, you could think of absolute value of X, make his own little table. You know what I mean? With your -2, -1, 0, 1, 2. And when you plug into absolute value of X, remember you keep the numbers, sorry, but you make it positive. So that's where my V comes from. Okay, let's keep going. Distortions. All right. Technically, our book calls these the non-rigid transformations because the graph, the shape does not stay the same. And that's where all the size come in. However, before we start really grappling with this, let's at least talk about, does the outside, inside still work? Yeah. If we're multiplying by a number, technically a positive number, because remember the negative we think of as a reflection. He's kind of separate. If there's a negative number being multiplied, the negative means one thing and the number means something else. So we're saying just if there's a positive. On the outside, vertical stretch, and it's the way that we think. And technically the book puts it one way. I want to kind of give a little shortcut for each. So when it says vertical stretch, technically it's by what we would say by a factor of, or by multiplying And since it's on the outside, vertical, we're changing the y values, so the y's get multiplied by c. And to be honest, it's the way that you would think to do it in the sense of if 2 is on the outside of the y's, all the y's get doubled. Everything is twice as high or twice as low. The horizontal one, though, just like the shifts, are backwards of what you would think. Let's say dilation. Instead of multiplying by c, we multiply by the reciprocal of c. And we're multiplying technically the x values by that 1 over c. So it's backwards what you think. If you see an addition inside a function, that means to the left. If you see a subtraction inside a function, it means it's going to the right. Kind of same thing with dilation in the sense of you see the c, but we have to think about the 1 over c. And we'll see an example. There were a lot of c's in that statement. In just a second. I'm going to go ahead and change this by dilation as well. And the reason I'm changing it is sometimes it's going to stretch it and make it bigger, wider, taller, but sometimes it's going to shrink it and make it shorter, skinnier, etc. Okay? So what if we were to take something like, what's one of the easiest parent functions? Like the parabola? I think so, right? Let's take x squared. Do we have our clues kind of written down? All right. Ah, wait, no, I want an example. Stop. Okay, insert blank paper.
That's good.
That was close. Did I not update your board? Oh, I didn't. We're doing 1-7 with homework 1-7 due tomorrow. Example. What if I was to say, graph let's do 2 different ones. Let's do f of x is equal to 5x squared. And let's do g of x is equal to why did I do this one? Some of you mathematical ones are like, wait a minute, there's another way to do it, and you're totally right, and there's a really good point to that, so hold on.
Is this a section that will have like the most wording problems? Just because it keeps telling you how to build a graph, like horizontal.
Kind of,
stretch.
but they're not going to really tell you how. They'll probably give you an equation and have you analyze it. So the problem will be short, but maybe the answers sometimes are long. We have our normal x squared, right, guys? Left 1, up 1, left 2, up 4. Question, what's going to happen for the first one when I try to graph 5x squared? It's going to stretch. It's going to get steeper. What am I going to do to my y's? What y is here? 0. Times 5? Still 0. That's easy. But what's going to happen here? What was the old y? 1. And what is it now? Oh, and then that was -1. Sorry. We can go 5 here as well. It's a little bit higher. Uh-oh. What just happened? He got vertically stretched by a factor of 5. So all the y values, if I have points, I can just multiply the y's. The x's stay the same. There's still a point at 1. But instead of going up 1, now he's going up 5. Now what's going on in the next one? I could say horizontal shrink by 1/2. But what does that mean? 2 was at 4, right? Cut 2 in half, now 1 is at 4. 2 is at 4, sorry, that was -2. Now 1 is at 4. But what is that the exact same thing as? The horizontal shrink ended up to be a vertical stretch. Interesting. You could say it 2 different ways and they're both right. Now that's with a squared function. Some other ones, when you have a square root, maybe you can't do the whole like, hey, it's the same thing as, because you can't simplify. But if you can simplify, maybe there's more than one way of saying it. I want you guys to go play around tonight, section 1-7. I apologize, I didn't change the backboard. I forgot about you guys for some reason. Homework number 7 due tomorrow, but can transformations get hard?
Yeah.
So come tomorrow with questions that we can go over, okay? And we'll dig a little deeper on ones that have all of them all at the same time, and how do we figure out which one to do first or second or third, etc. But go tackle that homework tonight, due tomorrow, attempt it, and we'll try to work out the kinks.
Is this
Tomorrow.
one like yesterday's
Well.
with like solve problems, or is
There's
it
not
like,
very many tonight, did anybody look at
or
it?
is it like 1-4? There's
I
like
think it's kinda
30.
short, I think it's like less than 20, maybe even less than 15. Not many. Go have fun, bye guys.